Number 15, which will experience the greater effective nuclear charge? The electrons in the N is equal to the 3 shell of argon or the N is equal to 3 shell of krypton? Which will be closer to the nucleus? Explain. Okay. So with argon, we've got a neon core blocking the outer electrons from filling the nucleus. So there's a certain effective nuclear charge with 18 protons trying to hold on to that third energy level. When we're looking at krypton, we have 36 electrons pulling. And if we're talking about electrons in the third energy level, we still only have a neon configuration blocking. So with more protons pulling, those electrons are pulled way tighter and held way closer. So if we're talking about the valence shell of krypton, that's the fourth energy level. That third energy level is part of the core electrons. And core electrons are held way tighter and are pulled way closer than valence electrons. So there's your explanation. Number 25, use only the periodic table to arrange each set of atoms in order from largest to smallest. All right. So the trend on the periodic table is you increase as you go from right to left across the period, and you increase in size going down a group. All right, so as you go down into the lower left-hand corner, right, francium, that's the biggest, puffiest atom, and helium is the tightest, littlest atom up in the upper right-hand corner. So that's how it works. So if I'm comparing cesium to potassium to lithium, we're going down a group. All right, so cesium would be the biggest atom, potassium would be the next biggest, the smallest would be lithium, as we add more and more core electrons and shielding, blocking those outer electrons. So a bigger cloud with cesium than lithium. If we're looking at lead, tin, and silicon, it's the same thing. As you go down a group, you're adding shielding, you're adding core electrons. So lead would be the biggest atom, silicon would be the smallest. If we're looking at fluorine, oxygen, and nitrogen, we're talking the same amount of shieldings, and we're talking about more protons than the nucleus pulling, more effective nuclear charge. So the tightest cloud, smallest cloud would be fluorine, and the biggest would be nitrogen. So that's the trend. 29. In the reaction, right, so we've got the red ball reacting with the blue ball, and we've got the red ball shrinking and the blue ball poofing out a little bit. Which sphere represents the metal? Which represents the non-metal? Explain your answer. All right, so if the red ball is shrinking, it's because it lost electrons. That makes it the metal. So red ball sodium reacting with blue ball chlorine. The outer electron of sodium gets transferred to the outer level of chlorine. Therefore, you've lost your third energy level with sodium, so you get a drastic decrease in size with the cation formation. And you add an electron. You get more electron-electron repulsion in the outer level of chlorine, well, chloride. So the cloud puffs up a little bit. If we're looking at that in terms of how it affects the electron configuration, the outer electron in the 3s of sodium gets transferred to the empty or the half-filled 3p shell, 3p orbital of chlorine. And we lose our outer shell with potassium, so cations get way smaller, tighter clouds, no more valence electrons, and with anions, they puff up because there's more electron-electron repulsion in the valence shell. Uh, 33. Some ions do not have a corresponding neutral atom that has the same. Some ions do not have a corresponding neutral atom that has the same electron configuration. For each of the following ions, identify the neutral atom that has the same number of electrons and determine if this. Excuse me, class. My daughter is making noise in the background. Quiet, please. Quiet on the set. Things I put up with. All right, if such an atom does not exist, explain why. All right, so we're comparing chloride. Does chloride have a isoelectronic neutral atom? All right, so if we're comparing chloride to argon, right, you put an extra electron into chlorine and make chloride. All right, so this is the electron configuration for chlorine. There's one more electron space left in the 3p. So you put an electron in there, and now you have the same electron configuration as argon. So argon and chloride are isoelectronic. They have the same electron configuration. If we're looking at B, well, there it is. All right, so we put the extra electron into chloride, which gives us the same number of electrons as argon. If we're looking at B, scandium 3+, in order to get a 3+ charge on scandium, we have to remove the 4s electrons first. All right, so it's a transition metal. We've got one electron in the 3d and 2 electrons in the 4s. So once we remove those 2 electrons from the 4s, we now have a +2 charge. We have an argon core with 1 electron in the 3d. If we remove that 1 electron from the 3d, now we have an argon configuration. So scandium 3+ is isoelectronic with argon, and they have the same electron configuration. If we're looking at iron 2+, there's 2 electrons in the 4s, and if I remove those, I now have 6 electrons left over in the 3d. So no, there is no atom that is neutral atom that's isoelectronic with iron 2+. So this is the thing with transition metals. Even though we put the electrons into the 4s first, because it's lower in energy, the 3d are on the inside. The 4s are the valence electrons, so they're removed first. So when we get argon 2+, iron 2+, it's not isoelectronic with argon. If we're doing the same for, if we were comparing iron 3+ to argon, right? This wasn't part of the problem. We'll call this, right, there it is. So iron 2+ is not isoelectronic with a neutral atom. If we're looking at C.5, right, I made this one up. I want to do iron 2+. I'd be digging that 1 electron out of that's paired up in the 3d. That's the one that would be removed to give me a 3+ charge. And again, iron 3+ is not isoelectronic with any neutral atom. Same with zinc 2+. It's the 2 electrons removed from the 4s that gives me an argon core 3d10 for zinc 2+. Not isoelectronic with any neutral atom. And if we're looking at tin 4+, it's the 4 electrons removed from the 5th energy level, right? The 2 come out of the 5p first, and then out of the 5s to give me a krypton core 4d10. So again, not isoelectronic with any neutral atom. You are very distracting. I am trying to say something complicated. Can you see what I'm saying? Not isoelectronic with a 4s of the 3d and the core electrons? It's hard to say. Stop playing with the dog. Number 39, write the equations that show the process that describe the first, second, and third ionization energies of aluminum. Which process require the least amount of energy? Okay. So this is aluminum's electron configuration. All right, so we've got a neon core, and the outer electrons in the 3rd energy level are in the 3s and the 3p. So if we're going to remove an electron from aluminum metal to form aluminum cation, the first electron that's going to be taken is the one in that 3p. That's the most shielded shape, right? The highest energy shape and the easiest one to take. So that's the first one taken off. So it's taken off to form aluminum plus ion, right? So this is the equation for the first ionization of aluminum to form aluminum plus. And that's the way they come off. They come off in a sequence of, they come off one at a time in a sequence of equations, right? So the first electron coming off has a certain energy requirement, right? A certain delta H. So they're all endothermic. You've got to put energy in to knock electrons off. So the first electron is knocked out of the 3p, and you have a plus charge on aluminum. Well, there's still electrons left in the third energy level. So aluminum plus is now losing an electron to form aluminum 2 plus. And that electron is going to come out of the 3s. Now, there's less electron repulsion as you take electrons out of the third energy level. So having less electron repulsion means it's harder and harder to take electrons. So to take that next electron requires more energy. So subsequent electrons are harder and harder to take. Now if you try to take that last electron out of the third energy level, that one has no electron repulsion in that energy level at all. So it's even harder to take out. It requires even more energy. And you're left with aluminum 3 plus. All right, so this is in part of the problem. But if you were to try to take an electron away from aluminum 3 plus, now you're digging electrons out of the core electrons, which are far less shielded than that third energy level. So to make aluminum 4 plus, you'd have to dig one of the electrons out of the core, right, out of that 2p, that neon configuration. And that would cost you a huge amount of energy. So this is why it doesn't happen. You don't find aluminum 4 plus in nature because the energy requirement is just too high. What is the relationship between the ionization of an ion with a negative charge such as fluoride and the electron affinity of neutral fluorine? All right. So if we're going to knock an electron off of fluoride to make fluorine, it costs you energy, right? It costs you 328 kilojoules. So turn it around. Fluorine taking an electron to become fluoride. That's just the reverse process. And instead of being endothermic, it's now exothermic to the same magnitude. So as we know, in a predictable universe, the reverse reaction, you just change the sign. It's the same magnitude of energy. So you'd release 328 kilojoules. Now the problem a lot of people seem to have, or at least maybe I had, was recognizing that the ionization of fluoride to make fluorine is not the same thing as the first ionization energy of fluorine. If I try to take an electron away from fluorine to make fluorine plus, that's going to be a way greater energy requirement. So whereas the two are the reverse of each other, this thing is totally different. You're talking about taking an electron away from fluorine to make fluorine plus. So this is not the reverse. This is a different animal entirely.